Hello YouTube and welcome to my channel. Today is an exciting day for me. I have the first or maybe the last step of the build that I'm working on right now. I'm working on a home-built CNC router. Kudos to YouTuber Strange Garage, who has a series of YouTube videos on how to build a $500 CNC machine.
I could probably build a CNC machine.
He's the gentleman that got me motivated. It also helped when I was digging around the garage. I found a box of old controls that I was going to build the ultimate CNC machine. So my cost went down considerably. It turns out I had 4 stepper motors and 4 Gecko drives, the Gecko 201 micro-stepping drives. In their day, these were very expensive and they're still worth about $150 each. So I'm hoping to build this for less than $1,000 total. And for me, because I have the electronics already, probably around 500 bucks or less. So if this sounds interesting, follow me along as I explain my Z-Axis. First, let's take a look at what a CNC machine is. CNC stands for Computer Numerical Control. That just means that the computer can control motors which convert usually rotational motion into linear motion. It drives different axes, so you've got an X, a Y, and a Z. X is left and right, Y is back and forth, and the Z-axis is up and down. So if you look at this website here is the image of Z, up and down. The X would be moving back and forth, and the Y would be doing the opposite. So you can see the machine is just moving, in this case, the stock. Mine is going to be moving the gantry, which is this, and it's going to be moving it back and forth. And the Z is going to be moving up and down on a little sled. That's pretty much it. The spindle is usually a router. It can be a rotozip, it can be a Dremel, and it can be one of those cheap Chinese 500-watt spindles. The entire CNC router is primarily made out of 1.5 inch by 1.5 inch angle iron. This is commonly available and relatively inexpensive. I bought 10 5-foot lengths for about $80. Then I promptly ran out and had to buy some more, and the price went up because of COVID to $100 for the 10. So you figure about $10 Canadian for one 5-foot length of 1.5 by 1.5. I think it was 1/8 inch thickness. After cutting it, you have to take off the burrs and make sure that you've taken all the sharp edges off to make it finger friendly. And here I am doing that. We need to make the linear bearings. The Z-axis requires 2 linear bearings, one for either side, that are tied together with a 3/16 steel plate. We are also going to need a set for either side of the X-axis. So I figured it'd be good to make a template. If you can see here, I've got a 12mm and 32mm hole set up in a self-made little square bracket. Making a template makes it easy to replicate the drilling pattern on all the stock. After you've scribed your mark on the steel, you want to use a center punch to punch your location for drilling. This allows the drill bit to start without wandering, making for a nice, clean, perfectly aligned hole. Start off with a small bit. I think I started with a 1/8 inch. That gives you a pilot hole for the larger bits that are going to follow. When you're drilling steel, you want a slow speed and, if possible, use lubricant like oil. Tapping fluid would be okay as well. For the Z-axis, we are going to need 2 pieces of angle 6 inches long. In each piece of angle, we are going to require 5 holes. So for the Z-axis, we will need a total of 10 6mm inside diameter bearings. When you're done drilling and countersinking your holes, now it is time to install the 6mm bearings. Here's a quick tip for you. I am using 6mm bolts to fit into the 6mm inside diameter bearing. The shaft head is a 10mm hex head. Grab an old 10mm socket, weld a washer to it, paint it red so you won't lose it. Now you've got a quick adjustment tool for when you're tightening these bearing fastening bolts. The motor mounting plate is 3/16 inch steel. I needed a 6 7/8 inch wide and 6 inch high piece. You can use a plasma cutter, angle grinder, or any other method to cut the steel. I found the plasma cutter was easiest. Take a look in the description below for a link to my video on how I made my inexpensive plasma cutting table. All of the NEMA 23 stepper motor mounts are made out of 3/16 steel stock. Mounting plate on these motors has a small dimple of about 1.5 inches, so you need to drill 1.5 inch hole to properly mount them. Sadly, I don't have a way of drilling 1.5 inch hole through the steel, so I'm just going to drill a hole for the shaft, and I will butt that little extrusion against my steel plate. After the plate was made, I welded it to a piece of angle so that I could bolt it to my Z-axis assembly. In order to get the holes lined up properly for the bolts, I used a transfer punch. If you've never used these before, you should get a set. They're inexpensive and allow you to accurately transfer the location of a hole to your stock. There it is. The beast. Solid steel Z-Axis, complete with a NEMA 23 motor, and I have a luggage scale. Let's see how heavy this puppy is. That is almost 6 kilograms, or about 12 pounds. That's a solid piece of equipment.
Let's do some measurements of the actual Z-axis. The sled that holds the spindle is 15 centimeters, or approximately 5 7/8 inches tall. It is 17.5 centimeters wide, or approximately 6 7/8 inches wide. The full length is approximately 30 centimeters, or 11 3/4 inches. And the width of the rails is 16.5 centimeters, or roughly 6 3/8. The length of the ACME screw is approximately 30 centimeters, or 11 7/8.
Here you can see the welded channel that I've made. Right here we can see the 1.5 inch angle, the bearings, and that would be the anti-backlash nut on the 1/2 inch -10 ACME threaded rod, pillow bearings, flexible coupling to the NEMA 23 motor. Here we can see that I've welded on the 2 pieces of angle to give me an approximate height of 6.6 millimeters, or 2 5/8 inches. And here you can see the welding detail of how I put the 2 tracks together. I also bolted on the NEMA 23 mount, so there's a little bit of adjustment in case I didn't have my alignment correct. Here you can see I've got 24 volts DC, minimal current draw. The Gecko is on. We're getting a flashing LED on the USB CNC controller. That indicates everything is well. And now we'll see whether we can make this thing move for the first time. Here are the Z-axis motor movement profile that I've started with. I'm using 2,000 steps per inch. I'm using 200 inches per minute on the velocity, 5 inches of acceleration, and a step pulse of 1 microsecond and a direction pulse of 1 microsecond. We'll see how that works. Probably need to adjust it. So we'll say OK to that, reset that, Now we'll use the page up and the page down button and see what happens. Here's page up. Here's page down. I think we can do better. I'm going to increase the speed and we'll come back once I've done the settings. Here's a very quick test, not very accurate. I'm going to be using a set of calipers to determine the repeatability and accuracy. But right now I'm just using a standard steel rule. I've got it set at 4 inches on this corner. I'm going to tell it to run. I want it to plunge 1 inch down and then return back 1 inch. So let's see if it can do that. That was with a feed rate of 25 inches per minute. That wraps up the test of my new Z-Axis for my awesome all-steel CNC router. I will be documenting some of the other build processes along the way. The next video will likely be how to build and configure an auto height tool or touch plate. I hope you enjoyed the video, and if you wouldn't mind clicking the thumbs up and maybe even subscribe, I'd really appreciate it. Thank you. Have a great day.